Now we come to the creation of individual short lull pulses, and we are going to welcome Professor and Director Ferenc Krausz. So please join me in welcoming him.
Thank you. Let's see. Good morning, ladies and gentlemen. It is a tremendous honor to be here, and I thank the Royal Swedish Academy for bestowing it on me. It's still hard to believe. I would also like to thank all persons in my life who supported me, helped me learn, grow and achieve, my family, my teachers in Hungary, my co-workers in Austria and in Germany, and our collaborators from all over the world. Some of them will show up on my slides, and I already now cordially thank them, as well as the many more who are not going to show up, for their invaluable contributions, without which I would certainly not stand here today. These two gentlemen played a very special role. I owe them very, very special thanks and gratitude. Arnold Schmidt's guidance and Paul Korkum's deep insight into electron phenomena have profoundly and decisively influenced my path. This lecture is going to be devoted to how attosecond physics opens the door to the world of subatomic motions of electrons, which were inaccessible to human observation until the turn of the new millennium. For decades after following its discovery, this elementary particle was thought, when bound in atoms, to be revolving around the nucleus. Eventually, quantum mechanics revealed that subatomic motion can only emerge by exciting an electron from its ground quantum state to a superposition of stationary states, and the resultant temporal variation of the electron's probability density constitutes the closest analogy to classical motion, exemplified here by the dipole oscillations in the 1s2p superposition state in hydrogen. One of the messages that I would like you to take home from my lecture is that control is absolutely central to time-resolved observation and exploration. For example, the control of electrons' current by transistors in macroscopic nanoscale but yet macroscopic circuits with microwave electric fields underlies the capturing of fast-varying electronic signals in macroscopic circuits. Analogously, the control of electrons' current by the electric field of light opens the door to observing and eventually even controlling electron phenomena in atomic and even subatomic dimensions. But how actually to control the electric field of light in order to be able to control with this controlled force that it exerts on these electrically charged particles to control the atomic scale electron current. 4 Nobel Prize winning concepts paved the way. Lasers utilizing nonlinear optics and chirp pulse amplification can yield ultra-short, very powerful ultra-short pulses. Whereas the control of the laser frequency comb can lead to pulses with a controlled waveform. Controlling the waveform of light actually means that we have to shape, we shape the electric field within its oscillation period. What does this mean? Well, what it technically requires is an octave spanning bandwidth. Lacking lasers with such a gain bandwidth, we have no other choice but try to broaden the spectrum of the pulses outside the laser. And that's exactly what we can do in a wonderful device invented in Milano by Orazio Suelto, Santo De Silvestri, Mauro Nisoli. We can send a short laser pulse through a gas filled hollow fiber where it suffers, it is subjected to cell phase modulation, and this nonlinear process broadens its frequency spectrum. The result is a pulse that carries a frequency sweep with a strongly broadened spectrum, and these pulses can subsequently be compressed by another wonderful device, chirped multi-layer mirrors invented in Budapest by Robert Zippert and Karpat Ferenc. And these two devices together are able to actually advance femtosecond technology to its limits, to the limit that is imposed by nature, to the limit of a single wave cycle. So thanks to these two technical developments, powerful pulses consisting of a single intense oscillation cycle became available with controlled carrier envelope phase since 2003, and with this latter development they actually opened the door to precision attosecond metrology. But before I come to that, I just would step back a couple of years to briefly review the first attosecond generation and measurement experiment in Vienna. The multi-cycle driving laser pulses used in the experiments of Anne and Pierre were replaced by pulses comprising a single wave cycle, single very intense wave cycle. When focused on atoms, the extremely rapid turn-on in these pulses implies an unprecedented rate and temporal confinement of ionization, and as a direct consequence, a very short, very brief emission of XUV light from the higher order harmonic generation process, particularly if we filter the highest order harmonics, in our case, with a bandpass multilayer, which also focuses the beam to a second jet of neon gas, where the XUV pulse knocks electrons free in the presence of the few cycle laser field, and actually provided the first very strong experimental indication of the existence of an isolated sub-femtosecond pulse in a series of experiments performed by Michael Henschel and Reinhard Kimberger in our laboratory at that time at the Technical University of Vienna back in 2001. A couple of years later, laser pulses with controlled waveform enabled precision attosecond metrology by implementing an ingenious concept of Paul Corkum, the concept of a light field-driven streak camera. The XUV pulse again hits neon atoms, again in the presence of the laser field, but this time we measure the time of flight of those electrons which are catapulted from the atoms parallel to the direction of the laser field. Depending on the moment of release, the laser field accelerates or decelerates them. And you see here from this equation that now physics further simplified after the electron is liberated. The laser field is so strong that actually we can describe the motion in a very good approximation classically. Just Newton's equation is being solved here to calculate this delta P, which is the kick in the back of the electron to move it faster or slower. And this very kick is depending on the moment of release, and this actually maps the temporal profile of the XUV pulse to a final momentum distribution of photoelectrons. Recording this XUV-induced laser field streaked photoelectron spectra as a function of delay results in a spectrogram which allows unambiguous complete retrieval of both the laser waveform as well as the complex amplitude of the attosecond XUV pulse. So this experiment actually demonstrates how control enables observation, this time on an attosecond time scale, and actually renders the basic tools, the attosecond varying force that this light electric field exerts on electrons, and the attosecond duration XUV emission available for real-time observation and control of electron light phenomena. With these tools in place, we can set out to perform attosecond time-resolved spectroscopy. You have learned from the wonderful talk of Anne how actually such spectroscopy can be done by using XUV pulses to kind of trigger the motion, like ionization, and use the basic laser field to capture the motion, right? Here I turn the game around and I will show you an example where we use actually the attosecond varying and attosecond controlled force that our single cycle laser pulse exerts on electrons to trigger the motion, and use the attosecond XUV pulse to actually capture it, to take the snapshots with a delay and try to reconstruct the motion from this series of snapshots. So basically we just use this single cycle laser field to ionize an atom, actually in the same focus which we used before to characterize the tools by attosecond streaking. And this time we put some other gas there, krypton gas, and the single cycle laser field actually ionizes this gas. And we send the XUV pulse with some delay through the ionizing medium and analyze its spectrum. It's the energy distribution of the photons contained in this attosecond XUV probe. And when the system starts ionizing, then we see some changes in the spectrum, And that's what, with the help of some theory, as we will see in a moment, gives us information about how the electron is actually liberated and is coming out, is catapulted out of the atom. So obviously, this kind of measurement is able to provide direct time domain insight into what I think can be considered arguably the most fundamental strong field phenomenon, optical field-induced electron tunneling. Here we can observe how this process, in this case in krypton atoms, is substantially confined to the central wave cycle of a cosine-shaped near-infrared waveform, which we have measured simultaneously by attosecond streaking. So remember, two attosecond techniques are being employed in this very experiment: attosecond transient absorption spectroscopy, which leads to the transient absorption spectra I'm going to show you in a moment, and simultaneously attosecond streaking to learn precisely at which moment actually, or what is reference in the time, on the time scale, what is the time zero with respect to which we delay our attosecond XUV pulse. One of the exciting discoveries that we learned from this experiment was that the about 700 attosecond rise time of the ion population turned out to be significantly slower than predicted by the quasi-static A-decay theory. So this kind of non-adiabatic tunneling that could not have been discovered by any previous spectroscopy. When subjecting these krypton atoms to the strong field, actually the electrons can be liberated from two different so-called spin orbit quantum states of the 4p subshell of krypton with comparable probability. This means that the hole in the electron cloud of this krypton atom is created in a superposition state, because the hole can be either in one or in the other spin orbit state. Remember, we learned at the beginning of this lecture that putting the electron, or in this case the hole, same thing, in a superposition state means motion, subatomic motion. And indeed, the sequence of transient absorption spectra that is shown here in a false color representation does exhibit pronounced temporal variation, periodic temporal variation for increasing delay of the XUV probe. The 6 femtosecond delay period actually precisely corresponds to the 0.7 electron volt energy separation between the two spin orbit levels. To develop the film from these transient absorption spectra captured with 150 attosecond exposure, the photographer's job here is taken over by theorists, and I would very much like to join previous speakers, Anne and Pierre, to emphasize how incredibly important the role of theorists was in the emergence of attosecond science. So here you see the result of that modeling, and the excellent agreement between theory and experiment allows actually to reconstruct the attosecond snapshots of the whole density distribution versus time delay, and even the initial quantum phase between the two components of the wave packet of this hole that we create. So from all this information, we can completely reconstruct the subatomic motion following tunneling ionization. Here in a slow motion replay with a temporal magnification of 10 to the 15. When rendering these motions accessible to human observation, attosecond spectroscopy furnishes us with a temporal magnifying power that is equivalent to the combined magnifying power of a space telescope and an electron microscope. In the words of Eva Olsson, we can now open the door to the world of electrons. Attosecond physics gives us the opportunity to understand mechanisms that are governed by electrons. The next step will be utilizing them. But which applications are likely to yield, in the words of Max Planck, the richest and most lasting gains that we can possibly draw from this new perception? If you accept that this may be a right question, we have already mastered what Ernie Rubik considers to be the most important and difficult task, namely finding the right question. My tentative answers appear to be deep dives into the delicate details of light-electron energy exchange at the nanoscale and into the molecular composition of functional constituents, biofluids, body fluids, and tissues of living organisms for tackling contemporary grand challenges. Ever since the beginning of the new millennium, advancement of processor performance was driven by miniaturization, whilst the clock rate actually determining the speed of processing was stagnating at about 10 gigahertz. Can attosecond physics possibly contribute to exploiting the fourth dimension for further advancing electron-based signal processing? Another contemporary grand question relates to the millionth of premature deaths on this planet year by year, mostly in low and middle income countries. Most of these deaths could be prevented by early intervention following, of course, early detection of the condition, urging the quest for affordable health monitoring. Can the molecular composition of human blood provide sufficiently comprehensive information to serve as a basis for populational health screening, and can attosecond physics possibly contribute to that? In order to be able to tackle such questions, attosecond technology based on complex vacuum systems has to become simpler and more powerful. And few cycle, or actually single cycle light, recently enabled this, owing to its ability to realize the same process that we've just studied in atoms, actually in a wide gap solid, namely optical field-induced electron tunneling. But why is this extreme temporal confinement so essential here? Because no solid matter could otherwise survive the required critical field strength of about 2 volts per angstrom only by confining this extreme field strength to a single oscillation cycle can irreversible breakdown be avoided. Tunneling then occurs within a fraction of the central field cycle in a cosine-shaped waveform. This means actually, again, less than 1 femtosecond for visible or near-infrared light. Sub-femtosecond carrier injection replaces sub-femtosecond XUV light and thereby obviates the need for vacuum systems for a class of applications extraordinarily important for advancing electronics, namely the attosecond control and probing of valence and conduction band carrier dynamics. In a primary step, sub-femtosecond carrier injection is used for optical field sampling. By implementing it in a small volume, where the test field can separate the injected electrons and holes towards 2 electrodes and drive actually a current in an external circuit connecting these 2 electrodes. And here you see this current as a function of delay with respect to the red infrared test field, which is obviously measured with a good fidelity as confirmed by attosecond streaking. Now, this ability to precisely measure the oscillating field of light offers a new probe for attosecond phenomena in the form of the electric field of light, all the way from the infrared, meanwhile, to the ultraviolet. It can actually probe the arguably most fundamental consequence of any light-matter interaction, the displacement of electronic charge density, briefly polarization. It is embedded, it is inscribed in the electric field of the transmitted wave. Referencing this transmitted field to the input field actually allows us to unambiguously retrieve, at least for a thin medium, the induced polarization. Together with its driving field, it actually directly yields, by means of the simple formula, the rate of energy exchange between the field and the electronic system. If we now integrate this rate from a certain time before the electric field is coming in to a certain time point, then we get basically the transferred energy, and that's what I'm showing you here for an insulator and a semiconductor subjected to strong fields. For the highest field strength, the energy transfer appears to be completely irreversible. So basically the transferred energy just stays there after the laser pulse is over. But for reduced field strength, what we see is that actually the field can completely reverse this energy transfer. This is the yellow curve, at least for the 6-photon band gap. And this is a very important regime because such a reversible process is really ideal for dissipation-free ultra-fast signal processing. This regime is completely missing in the 2-photon band gap medium, where reactive and dissipative nonlinearities always appear in combination. These studies actually showcase how real-time access to the light electron energy transfer explores optimum conditions for ultra-fast optoelectronic signal manipulation. We have now seen how light field sampling and the oscillating light as a probe may help advance electronics. In the remaining, few minutes, I would like to address how the same technical capability provides access to minuscule changes in the molecular composition of human blood plasma, which is a sensitive indicator of health disease transitions. To sense these transitions, we propose, instead of searching for individual biomarkers, actually accessing the global molecular landscape via field-resolved spectroscopy. To this end, we expose human blood plasma, I should say, to a single cycle infrared laser pulse, which coherently excites molecular vibrations within its spectral band. The vibrating molecules in turn radiate coherent infrared waves in the wake of the excitation. The resultant signal, which you see here, is characteristic of the molecular composition of the sample. We capture this electric field molecular fingerprint with highly sensitive attosecond metrology. This fingerprint signal is expected to change whenever emerging abnormalities change the sample's molecular composition, which we recently verified for several chronic conditions such as cancer, cardiovascular, and metabolic disorders. As a prominent example, we compared 470 samples of lung cancer patients with the same number of samples of reference individuals free from cancer, briefly controls, with the two cohorts being carefully matched regarding the distribution of the subject's age and other parameters. These are the electric field molecular fingerprints of all those samples. Clear differences come to light between the two cohorts some 1,000 femtoseconds after the excitation peak, where molecular emission starts dominating over the excitation. we can now quantitatively analyze these differences in terms of the gaps between the adjacent zero crossings of the oscillatory signal, briefly half-cycle gaps. Here we show the mean and the standard deviation of the half-cycle gap, what I would call spectroscopic markers, more than 350 of them at this time, evaluated from the fingerprints of stage 1 to stage 4 lung cancer. From the fingerprints of the controls, and most importantly, the differences between the two cohorts. These cancer-induced signals, cancer-induced changes in the half-cycle gaps range from tens of attoseconds to a couple of femtoseconds. Here we plotted these lung cancer-induced changes in half-cycle gaps for different stages in comparison with the spread of controls. The efficiency with which a well-trained algorithm is capable of distinguishing cases from controls critically depends on this comparison. The classification efficiency can be improved either by increasing the disease-induced signal or by reducing the spread of controls. The cancer-induced signal increases for progressing stages, and so does the classification efficiency, the so-called area under the curve. These AUC values are promising for non-metastasized lung cancer. However, they could be even further improved by reducing the spread of controls, even at the current stage of development of infrared fingerprinting. And that's exactly what our computer modeling predicts for referencing each individual cancer fingerprint to a set of controls collected from the same individual before contracting the disease. The spread of these controls is much reduced, thanks to a strongly reduced within-person variability of the infrared fingerprints over time as compared to the spread in a healthy control group. We pursue proving the predicted performance in a longitudinal follow-up study in Hungary. The predicted above 90% detection efficiencies constitute unprecedented values for stage 1 to stage 4 lung cancer. The price to be paid for this early detection and thereby protection against being diagnosed with the deadly stage 4 will be a yearly blood test. The study in Hungary may reveal that infrared fingerprinting is able to screen other severe chronic conditions at an early stage, and consequently it will become affordable for screening whole populations, may save millions of lives year by year. I take the academy's decision as a mandate for the pursuit of this very goal with utmost determination. And as a mandate for exploiting our increased visibility for the benefit of the children in Ukraine who are already dreaming of joining in, like Vladislav from Lyceum number 10 in Marhanets, near the front line. Just as all other children anywhere else, they deserve a chance to realize their dreams. And we badly need all of them. We badly need all of them to carry on once our own time comes to an end. Thank you.